Welcome back to High Performance Computing Advanced Scientific Computing course, lecture 14. This is the part 2 of this lecture, and we will carry on about the talk about the solid object finite element method. We will have some example from the parallel computing application and a finite element method. The first example is nodal based finite elements. In the finite element, the matrix is sparse, so iterative method is used to solve the matrix system. In this example, these methods used to solve this problem. The conjugate gradient with diagonal. Each processor computes his part of the preconditioning matrix by inversion of the diagonal term of the finite element matrix. No message passing is required, and the memory space to store the preconditioning matrix is small. The second one, incomplete Cholesky, the decomposition of the finite element in two matrices. This algorithm is implicitly parallel because the Lij term can be computed independently once the diagonal Ljj term has been computed. Of course, the detail of this method could be read in the resources, and if you are interested, you can read about them. However, we only point to the main feature and the properties of this method and how it's used in this problem. And the third one is the block incomplete Cholesky preconditioning. This one is assembled only with the term stored on the considerate processor to avoid message passing during the building of the incomplete Cholesky matrix. As you can see here, how the message passing for the symmetric plane it's working, and there is a different categories applied here. First one is the symmetric planes, and then symmetrization, and the example is 4 processors. We can see how in this first figure how the node on the symmetric plane is working, but here there is a different message passing working, and here the solution is presenting the result with different number of the processor and how the speed up is working. The assembling with more processor, it has a like linear behavior, but the for the boundary condition and symmetrization, it's the speed up is going down. And here the detail of these three applied methods with the message passing interface MPI. The first one, we can see how it's working with the SPMD. The number of the processor, when it's increasing from the specific numbers, it's get constant values of the speed up. However, with incomplete Goletsky processor, we see there is a optimum number of the processor that has a best speed up, and with incomplete Goletsky processing, the speed up behave different, and of course the time is going down, so that means the speed up is going up. When changing the number of the storage 1 and 2, also the behavior here is presenting different for these three applied methods. So here this example mostly want to show the effect of the number of the parser, how it's working on the finite element method to solve the sparse matrix with iterative methods. Here it's another example from the distributed memory, and you can see how it's look like the distributed memory, and you know about this type of the configuration in the from the previous lectures. And here the flow of the solution of this type of the problem, and here the result of the speed comparison with different count of the finite element or meshes. Now let's have a look on the some 3D example. When there are three-dimensional, the parallel processing is essential, and the finite element involve really massive computing. Here is the example of the three-dimensional, so an elastic solid object, and it's a cube. And you can see how when the number of the meshes is changing, the mesh subdivision, how it look like with number of the equation. So here it's a very large number of the equation. To solve the equation, of course, we need the parallel computing to accelerate the solution and be able to do that. Solution performed with three setup of the meshes. These meshes 40, 40, 40, 100, 100, 100, and 400, 400, 400. You see the for all of the every of these mesh category, we know the number of the equation from the previous one. To see the impact of the solution with different parser, you see when the number of the parsers goes up, it's really reduced the computing. With 8 parser, the time is 96 seconds. With 256 is 5.5 seconds. Also, it's repeated again for another type of the another configuration of the meshes. And in this figure, we can see when the size it's the size of the meshes is going up, and what's happening when the number of the iteration ratio, how it's going with the computing. This is the iteration size versus the problem size. This is another 3D example for the Laplacian flow. Uh, and we see with these configuration of meshes 200, 200, 200, and with different number of the processor 8, 16, 32, and 42. The time of the solution or the number here is presented. The solver take this time, and the analyst take this time. And the number of the equation, we can see when we have 125,000, the iteration required to be convert 72 with 8 million equation, 180 iteration is required to converge to the right solution. And we can see the parallel computing has a remarkable effect to reduce the time. For example, when it's going from 8% to 64, here the time of the analysis it's get around half, from 164 to 86. This is another example from the three-dimensional transient heat condition with implicit analysis in time. Uh, as you can see, the mesh size here it provide different detail. Uh, Here, this close-up of the surface of the meshes, you see how it look like from the close-up, and for every meshes, if we choose different size, we will have different detail because the solution is coming from these nodes. Here, with meshes 100, 100, 100, changing the number of the processor from 16 to 64, the analysis time from 385 to 101 and 108 seconds. And here it's presenting with number of the ampere processor, how the time it's reducing effectively. And the solution, of course, has a very good result close to the ideal one. This is another three-dimension example, which is applying the finite element method for steady state Navier-Stokes analysis. This example has could be solved with different number of the element. As you can see, the different element number of the element has a different iteration to be converged. From the result, it seems they used 20, 20, 20 mesh, and the number of the MPI changed with 8, 16, 32, and 32. And we see with about constant iteration how it's going with the number of the analysis of solution for this problem. In this figure here, we can see how it look like with number of the MPI processor and the speed up, and difference between actual and the ideal condition, and so regarding the result, also there is a visualization with power view of this problem here, as we can see. From the finite element method, we had few 3D example, and the example was in for the solid object and for fluid dynamic area. So that means its capability uh, could be used in both area. However, depend to the problem, we need to select a correct method to solve the problem. However, in regarding the parallel computing, when we have a large problem, especially for the 3D types, with a number of the element and number of the equation, the iteration has required extensive computing, and we need the parallel computing to do that. So we can say the power and the capability of the finite element method has a direct relation to the computer power to be able to solve uh, extensive problem which large computation should be have access to parallel computing. If not, without the computer of the power, the finite element method is limited, and we cannot use it for every type of the problem. This is the key point regarding the requirement and the importance of the HPC in the numerical methods such as finite element methods. This is the last slide from this part 2 of the lecture 14, and I recommend you watch this video. This is the example of the application of the finite element for the vehicle aerodynamics, and it's one of the most interesting area in the fluid dynamic and the studying of the aerodynamic, it has a direct effect in many applications. Um Regarding the finite element in this course, we talked about the available technique in the finite element method, and indeed it's uh, applying now widely in the most software that we have in the finite element method. Of course, they're using this method. However, in the finite, for the fluid dynamic area, there are different software. In some software, they are using the finite volume method. In some other, they're using the finite element. It depends to the capability of the software and the application area. However, most of these methods for the research, you can create your code and you can solve the problem with desired condition. And it's possible to develop the code and the program for the aerodynamic in many use cases. Uh, so we have finished this lecture here. Here you can see the references that could be helpful for you if interested in this area. You can have a look and read more detail about the finite element method and how you can apply it. Thank you. See you in next lecture.